Jai Hind everyone. Today I, Anshul Kumar Panchbhaiya, Assistant Professor Mechanical Engineering Department AKGEC, is going to discuss an important topic in strength of material that is known as thermal stress. Today we are going to discuss this important topic named as thermal stress. It is one of the important topic as per competition point of view, as per GATE exam point of view, as per AKTU exam point of view. So let us begin this topic. Now, what do we understand by the term thermal stress? What is a thermal stress? See, whenever a component is heated or cooled, whenever a component is heated or cooled, its deformation starts. Its deformation starts. Now, if component is expanding, if component is expanding, then it is thermal expansion. And if component is contracting, this is thermal contraction. Now, we are totally focused on change in temperature. As I have mentioned in the beginning, that whenever a component is heated or cooled, means if we are heating a component and if we are cooling a component, means we are changing its temperature. Suppose that initial temperature of any component is Ti and we are changing its temperature to some temperature like Tf, final temperature is Tf. Now that delta T change in temperature will be Tf minus Ti. So that's why I have said that whenever a component is heated or cooled, its expansion or contraction starts. Either it is going to expand or either it is going to contract. If it is expanding, then it is thermal expansion. If it is contracting, that is thermal contraction. Means thermal word if we are hearing, then we must focus on the term temperature. So thermal stress is totally depending on the change in temperature whenever a component is heated or whenever a component is cooled. Now what we are going to do here, we are going to assume all bodies to be cylindrical. All bodies to be cylindrical with a circular cross section. It's an assumption with a circular cross section. With a circular cross section. So, like this. This is a cylindrical body with a circular cross section. This cross section is circular in nature. Now, suppose if in this figure, what I have done, I have heated this body. Because in the beginning I have said that what is going to happen whenever there is a change in temperature. Produce expansion and contraction of material result in thermal strain and stress. Now, if I have heated this body and suppose the body is having, cylindrical body is having the length L, after heating its length changes to delta LT. This is delta LT, means change in length due to temperature. If I am writing its delta LT, that means change in length due to temperature. Now, if I say that I am writing it in the big at the top, if I say that then what will be the thermal strain? As our knowledge says, strain is change in dimension upon original dimension. Now, if I am writing thermal strain, that is epsilon T, then it will be change in length due to increase in temperature upon original length. Delta LT by T or delta LT by L. This will be known as the thermal strain. This is known as thermal strain. Now, what we got from this entire concept? That thermal strain is nothing. It is change in length due to temperature, increase in temperature upon original length. Now, that means we can say that epsilon T thermal strain we are getting whenever there is a change in temperature. Means if change in temperature is delta T, then epsilon T is proportional. Means whatever the changes we are getting it due to change in temperature. So if epsilon T is the thermal strain, then delta T is change in temperature, directly proportional. Then we can say, if I remove this proportionality sign, I am writing a proportionality constant known as alpha. This is delta T. This alpha is known as coefficient of thermal expansion. This alpha is known as coefficient of thermal expansion, or we can say coefficient of linear expansion, because the variation is in linear direction. Now, this term is very important for our concept point of view, because whenever we are solving the numerical, we are writing, we have been given with the value of alpha. So if we are having alpha and we are having a change in temperature, then we can write alpha epsilon T is equal to alpha delta T, because epsilon T is directly proportional to the change in temperature, and this alpha is known as coefficient of linear expansion. This has been written here also, alpha delta T. So what we are going to take as a sign convention, that whenever there is a thermal strain and we take, whenever there is an expansion, we take it as a positive quantity, and contraction we take it as a negative. Means if we are calculating thermal strain and if we are having a expansion, then we will take it as a positive, and if we are having a contraction, we will take it as a negative. I hope you are all clear with this concept. There are some important points from this page, that change in temperature is proportional to the thermal strain. Thermal strain, whenever proportionality sign is removed, alpha is introduced. Alpha is coefficient of linear expansion. Means whenever we are heating or cooling any body, means we are changing the temperature from initial to something like Tf, then delta T will be equal to Tf minus Ti. Then we can say that epsilon T is proportional to delta T, because thermal strain is introduced only because of change in temperature. Okay, this is the concept, and this is the formula for calculating any thermal strain, which I have mentioned it here also. Now, if I move further, what is a thermal stress? Before going through this concept of thermal stress, let us assume let us go through some basic concepts. Now, in previous slide, I have calculated epsilon T as alpha delta T. That means alpha is equal to epsilon T by delta T. Alpha is equal to epsilon T by delta T. And one more thing is there. Alpha is a linear expansion coefficient, and its unit is per degree centigrade. Its unit is mentioned is per degree centigrade or per degree Kelvin. Now, we know epsilon T is equal to alpha, epsilon T is equal to alpha delta T. Now, if I am writing that epsilon T is equal to alpha delta T, and in the beginning we know epsilon T is nothing, it is change in length due to temperature upon original length. If I replace the value here, what I am going to get? Delta LT by L is equal to alpha delta T, or delta LT will be equal to alpha delta TL. This relation we are going to achieve. What is this? This is change in length due to change in temperature. What we are going to say? This is change in length due to change in temperature. जब भी हमने जैसे whenever we change the temperature, we are getting the change in length. Now before going for thermal stress, now we have gone through this concept and we achieved a relation that delta T is given by alpha delta TL. Delta T is given by alpha delta TL. Now see, suppose there is a body and we are changing its temperature, and the body is free to move, free to expand, free to expand. That is a free expansion. Now in case of a free expansion, whenever a body is free to expand, then in that case, in case of free expansion, if a body is free to expand, that means there is no restriction. If there is no restriction, that means there is no thermal stress. That means sigma 2 will always be 0, only in case of free expansion. But what happens? What happens when there is a restriction? What happens when there is a restriction? Now we will see that if there is a restriction, we are saying if there is no restriction, it is a free expansion. It is a free expansion, then it is, we are having thermal stress equal to 0, no thermal stress. But if there is a free expansion, no free expansion, like this, I am having a cylindrical body and this body is fixed at both ends. We have fixed this body at both ends, and so cross section is again circular in nature, length is L, and we are supplying heat. Heat is being supplied here, means change temperature is being supplied here. Now I can say if initial temperature is Ti, final temperature is Tf, then delta T will be equal to Tf minus Ti. Delta T will be equal to Tf minus Ti. Now if suppose the body is free at the right hand side, from this end there is no restriction, and after increase in temperature the body comes to this point. Now this extra portion is obtained when we have freed this restriction. Now this, what is this? This is change in length. This is the amount. This is the amount which is been restricted by the support. The body is going to expand up to this point, but this is the amount which is been restricted by the support, like this. These are the supports which are restricting this expansion. That means if I say what will be delta L net, in this particular case delta L net will be equal to 0. Why 0? Because we have restricted this body from both ends. Now what is going to happen? What is happening here? We can say that free expansion is equal to constrained length or compression offered by the wall. We can say free expansion is equal to compression offered by wall, because this amount, this delta L amount, this amount is been prevented by P, this amount will be prevented by V, and we know from our concept that delta L is nothing, this is a mechanical force, then this delta L will be equal to PL by AE. This mechanical force is equal to PL by AE. Now here what we can say, what is free expansion? For free expansion delta LT, and for compression it will be delta L, or we can say, what we can say, that alpha delta TL will be equal to PL by AE. Alpha delta TL will be equal to PL by AE. Now this L and this L will get deducted. What I can write from here? I can write from here that if I just use the eraser, okay. If I write here, I write alpha delta T is equal to P by AE, or P by A is equal to alpha delta TE. Now what is this P by A? This P by A, we know is load upon cross-sectional area is nothing, it is stress. And this stress is the thermal stress. So this we get sigma T is equal to alpha delta TE. This we are getting sigma T is equal to alpha delta TE. So what we are getting from the discussion? We are getting from this discussion, whenever we change the temperature of a member, whenever we change the temperature of a member, its deformation is resisted when the member is fixed at both ends. Its deformation is restricted, and this restricted deformation set up a force or stress that is known as thermal stress. If there is no, what we have written, if there is, in previously what we have written, whenever there is a free expansion, then there is no thermal stress. But whenever there is a restriction, there will be thermal stress, and it will be given by alpha delta TE. So we are getting two results, final results, that whenever there is a free expansion, we have sigma T equal to 0 and delta LT equal to alpha delta TL. This is valid for free expansion. Free expansion के लिए valid है ये. This is valid for free expansion. But whenever there is a restriction, then there will be no free expansion. That means sigma T will be given by alpha delta T into E. I hope you all are clear with this concept, and this has been mentioned here. Sigma is equal to alpha delta T here. Epsilon T we have already discussed, alpha delta T. This is the relation which I am talking about. Whenever there is a restriction, there is a introduction of a thermal stress. And this is valid when the restriction is like this. A member is fully restricted. Then we have a thermal stress. Then sometime there will be a case. Sometime there can be a case when a member is partially restricted, like this. This is a partial restriction, and this particular partial restriction is known as yielding. This partial restriction is known as yielding, and this yielding distance is given by y. Now, if I say this is the length of the member and this is the part, so total length and final length will be given by L plus y. Now just see, whenever this length becomes L plus y, then only sigma T will develop. Whenever this distance gets 0, means this section reaches to this point, after that there will be a development of thermal stress. Till that point, before that point, there will be no thermal stress. Are you getting my point? There will be no thermal stress. Now, for solving this, what we are going to write? What we are previously, when there was no yielding, we have written delta LT equal to delta L. When there is a yielding, when there is no yielding. No yielding means fully restricted. But when there is partial restriction, then that will be delta LT minus delta L will be equal to that gap or Y value which has been mentioned in the question. I think you are getting the point. See, whenever there is a full restriction, this equation is going to be used. Delta LT will be given by, here delta LT will be given by alpha delta TL and delta L will be given by PL upon AE. But it will only be applicable for yielding when these two difference will be equal to gap. Means whenever there is a partial restriction, thermal stress will be induced when this restriction gets overcome. This yielding value will be taken fully covered by the member. Means total length become L plus Y. After that there will be a thermal stress. Before that there will be no thermal stress. See, so if I move further and I take this equation which I mentioned in the bottom, and I put it here, what is delta LT? It is alpha delta TL minus PL upon AE equal to Y. What is this Y? This is the gap. This is the gap. This is the gap. So what we can say, for fully restricted sigma T will be equal to alpha delta TE. But for partially restricted, we can calculate sigma T from here. P by A is nothing, it is sigma T, and if we sort out this equation if we sort it out, we can write sigma T is equal to alpha delta TL minus Y by L into E. So these are the two equations which we are going to use. The above equation for fully restriction, the bottom equation for partial restriction. I hope you all are getting this point, and this has been mentioned here. This is the entire concept of thermal stress. See, thermal stress is basically introducing in any member whenever there is a change in temperature, and there is a restriction also. If it is free to expand, then there will be no thermal stress. But whenever you are restricting the member from getting expanded or from getting contracted, then what you are doing, you are giving introduction to thermal stress. For restriction, there will be thermal stress. For free expansion, thermal stress will be 0. Sigma T will be 0 for free expansion. I hope you all are getting this point. So this has been mentioned here. Now, this is the relation between an axial stress, that is the thermal stress, and change in temperature. Alpha delta TE, and this is the relation. See, if in this equation Y becomes 0, that means there is no yielding, and there is no yielding, Y is 0, L and L get deducted, same relation you are going to obtain. So means no yielding means fully restriction. Fully restriction के लिए ये लगाते हैं, and ये वाला formula, this formula is for partial restriction. All right? Okay. See, what we have already seen this relation, delta T, which I have written as delta LT is equal to alpha delta TL. This is a temperature displacement relation. This relation is nothing, it is a temperature displacement relation. Now, what to discuss further. Whenever a problem come in thermal stress, it mainly deal with two cases, like there can be member in series and there can be member in parallel. Member in series and member in parallel. So what we are saying from this concept, let us consider a figure drawn below. Let us, to just have a feel of the concept, let us consider a figure drawn below. Suppose there are two members and which are connected in series. Now, if this member are connected in series, we can say this is alpha 1 and this is alpha 2. Coefficient of thermal expansion for this particular, this area is A1, modulus radius E1, A2, E2, this length is L1 and this length is L2. These two members are connected in series. Now what is the property of alpha? See, remember, always remember, if alpha is increasing, then always remember change in length will always be increasing, and if this is happening, then thermal strain will always be increasing. Alpha बढ़ रहा है, alpha is increasing, then rest properties, change in length, thermal strain is also increasing. Now, what is going to happen? See, both the members which are connected in series are fully restricted. Both the members which are connected in series are fully restricted. Now, if we see our previous knowledge, what our previous knowledge says, for fully restriction, delta L net will be equal to 0 because change in length is finally will be equal to 0. And what is this delta L net? This delta L net is nothing, is a delta L thermal minus delta L equal to 0. What is this delta LT thermal? It will be, we know delta LT is equal given by alpha delta TL. If we use it here, what we are going to write? We are writing like this: alpha 1 delta T L1, alpha 1 delta T L1 plus alpha 2 delta T L2. What is this? Minus P1 L1 upon A1 E1 plus P2 L2 upon A2 E2 equal to 0. This is we have written na, for fully restriction, whatever being restricted, it is the mechanical force which are restricting, and this is a thermal change in length due to thermal change in length due to temperature, delta LT. This is restricted by this, so their difference will be equal to 0. So this equation, now this equation you are saying we name it as equation 1 or equation A or equation 1, we can name it as a. Now if we say that from this equation, if the load is common, if load is common, that means P1 equal to P2 equal to P. So from this equation, you will be able to calculate the value of stress by using this equation. And whenever there is a yielding, suppose you have calculated the value of P from here, now thermal stress will be equal to P by A1 if area for A1, and sigma T is equal to P by A2 because load is common. Now sigma T1 and T2 will be calculated like this because you have calculated P na from this equation. L1, A1, even everything is given. You calculate P, use this equation, you calculate thermal stress. Now if there is an yielding, you are dealing with yielding, what is going to be happening to this equation? Nothing. Only if there is an yielding, for yielding, if there is an yielding, if there is an yielding. For yielding, summation delta L net will be equal to gap, whatever be the yielding gap. And this delta L net is nothing, summation delta L thermal minus summation delta L equal to gap. Previously this gap is equal to 0. So these equations are compatibility equations. These equations are compatibility equation. When gap is 0, this equation become equal to 0. That is also a compatibility. What compatibility? Whenever there is no gap. And this equation is also a compatibility equation when there is a gap. I think you all are able to understand the concept. See what we are doing nothing. We are doing simply, we are calculating delta LT, we are calculating delta L, we are taking their difference equal to 0 if there is no restriction. If there is restriction, sorry. If there is a yielding, then this concept. And equation is known as compatibility equation. Alright? Now, so see, thermal strength, same concept has been explained here. Strength, this is due to mechanical and this is due to thermal. Same which we have discussed previously. Always remember, when there are constraints, then the body experiences thermal stress. See, as in case of lateral strain, thermal strain do not induce stresses until they are constrained. Means if there is no restriction, there will be no thermal stress. Or there will be thermal strain, but no thermal stress. Thermal stress will always be there whenever there is a restriction. So this is mechanical and this is due to change in temperature. So we have discussed this previously. Members subject of varying cross section. I have discussed this previously just before. What is this? The entire concept. Delta L mechanical, PL upon AE. What we have written, na? But if there is no expansion, if there is no, we will write delta L net equal to 0 if both are restricted. Delta L thermal minus delta L mechanical equal to 0, and it is equal to gap whenever there is a yielding. So this has been explained here. Now this concept is being used whenever the members are parallel. Whenever the members are in parallel, how to calculate thermal stress? How to calculate thermal stress? Say, now to understand the concept, consider this figure. Consider this figure. Now, this is alpha A, alpha B, and again alpha A. We need to know all the members are having circular cross section. Now the length of the member is L. Now there are two material. This is material A, again this is material A, and this is material B. A material B is sandwiched between A. दो मटेरियल हैं, उनके बीच में B को हमने सैंडविच किया हुआ है. The material B is sandwiched between A. Now, what we are assuming here, we are assuming that alpha B is greater than alpha A. Means coefficient of linear expansion of material B is greater than the coefficient of linear expansion of material A. Now, if Ti changes to Tf and Tf is greater than Ti, then delta T is nothing, it will be equal to Tf minus Ti. See, initial temperature changes to final temperature Tf. Ti was the initial temperature. After supplying heat or changing in temperature changes to Tf. Tf is greater than Ti. Then delta T is nothing, it is Tf minus Ti. Now, what we need to remember, which the component having greater alpha, the component having greater alpha is going to expand more, and the component with lower alpha is going to expand less. Means if I draw an expansion diagram, so I can say the material B is expanded more, but material A is expanded less as compared to B, because only because the material with greater alpha, the material with greater alpha is going to expand more. Now, if I take an intermediate section in between these 2 points, I can say if this material B, this end point wants to reach to this axis, we are going to have a push on material B, and similarly at the same time we are going to have a pull on material A. Are you getting it? The section is in between them. This is the in between section. If this point wants to reach this point, then we have to compress it, push it inside, and if this point wants to reach to this section, we have to stretch it, we have to pull it. So we can say push on B equal to pull on A. Push on B equal to pull on A. That means push is force, force is stress into area. That means sigma B AB thermal will be equal to sigma A AA thermal. Sigma B AB thermal equal to sigma A AA thermal. And finally, this is the one, and the compatibility equation which you are going to use for the problem, this is epsilon A plus epsilon B will be equal to alpha B minus alpha A into delta T. Delta T. So these two equations you are going to use whenever there is a member in parallel condition. I hope you all are able to understand this concept, and in the further lecture we are going to discuss the numerical based on this concept. Thank you.